Hello. I wanted to show you a problem from your even more force and acceleration worksheet. Um, so the situation is this. All right. You have someone pulling a box across the ground. The box has a mass of 70 kilograms, and there's a rope or something pulling on the box directly. Okay. And the person's pulling. And we know the tension in the rope is 400 newtons. We know the angle that the rope makes with the horizontal is 30 degrees. Okay, so if that makes sense so far. All right. And we know the force of friction due to the surface pushing on the bottom of the box is going to be 75 newtons. So let's just see what we can figure out given that situation. So it should be obvious by now. First thing you would want to do is draw a force diagram for the box. And you got, let's see, you got weight going down. Okay, I'll try to make it larger. Weight going down. You got normal force going up. You got the rope pulling at this funny angle. That's 30 degrees above horizontal. All right, so I'll call that T, tension due to rope. You've got friction to the left. Okay, and I'm thinking that the horizontal portion of this 400 newtons is going to be bigger than my 75 newtons. So I'm going to guess that this system is going to have an acceleration to the right. Okay? Now, first thing you might want to do is calculate the weight. If you know the mass is 70 kilograms, the weight is going to be 70 kilograms times 10 newtons per 1 kilogram. That's on the Earth's surface that this is true. So you got 700 newtons is the weight. So this vector down looks like it's 700 newtons. This tension is 400 newtons. The friction is supposed to be 75 newtons. So I'm going to add these forces up. Let's see here. So I'll go, let's see. I'll start with friction to the left. So there's my friction. Now I'll have weight a lot bigger than my friction. So weight will go really far down because I know my weight is 700 newtons, whereas my friction is only 75 newtons. So there's my weight. And my tension due to rope should go up something like that, maybe. I'm just guessing. So there's my tension. And then my normal force should go up just enough such that I have a net force from where I started, which was there, to where I end. So my resultant vector should be to the right since my acceleration is to the right. Okay, so here is my net force vector, and I tried my best to sort of scale my vectors according to the numbers that I knew. They're not perfect. I just made a kind of a good best guess I could make. And main thing is weight is a lot bigger than my friction, and then the tension is also fairly large. All right, well, it looks like, let's see here. I could turn this into a triangle right here. Okay. And I know this angle here is 30 degrees. Okay. So let's see what sine and cosine can tell us. First thing is sine 30 degrees. You'll recall that sine is opposite over hypotenuse. So my opposite side is right here. And this side is going to be my weight minus my normal force, right? So sine 30 degrees is going to be my weight minus my normal force divided by my tension. Yeah, that looks pretty good. And let's see, I know my weight, I don't know my normal force, and I know my tension. So it looks like here I could easily figure out my normal force. So I'll go ahead and do that. Looks like T sine 30 degrees is equal to weight minus normal force, right? And it looks like normal force, therefore, is going to equal to my weight minus T sine 30 degrees, all right? Now at this point, I guess I can just plug in everything and figure out what my normal force is exactly. So normal force, now let's check this really quick. I added normal force to both sides of the equation, and then I subtracted T sine 30 degrees from both sides of the equation. So that looks good. 700 newtons minus, my tension is 400 newtons, and this is times 1/2, because sine 30 degrees is 1/2. And then normal force is therefore going to equal to 700 newtons minus 200 newtons. Yeah, that should be right. And finally, my normal force should be equal to 500 newtons. Cool. So I've now found normal force to be 500 newtons. Let's go back to our diagram and label the 500 newtons up, which makes sense that 500 newtons up would be less than the weight because part of the tension is directed upwards. So the tension that's directed upwards adds to the normal force to balance out the weight, okay? Because there is no acceleration up or down for the box. Cool. Well, sine was quite cool what it told us. Let's see what cosine can tell us now. All right. Cosine 30 degrees is going to be this length, which is my net force plus my friction, right? And I should realize that my net force should be my acceleration vector scaled by my mass, all right? I know my object's mass, 70 kilograms. That's sort of interesting. So cosine 30 is going to be my friction plus MA, because MA is the magnitude of my net force vector. That tells me how long it is. And this will be divided by the tension, which I do know. And the only variable in here that I don't know is my acceleration, right? I know my mass, I know my friction, I know my tension. I know what cosine 30 degrees is. Cool. So let's see what we can do. Well, we should be able to find A. t cosine 30 degrees is equal to friction plus ma, right? And then subtract friction from both sides of the equation. I get t cosine 30 degrees minus friction equals, and then I got m times a, right? And so I should have a equals t cosine 30 degrees minus friction all over m. And now I can tell you what a is now, right? A is going to be 400 newtons times cosine 30 degrees minus my 75 Newton friction, and all of this is going to be divided by the mass of my object, which is 70 kilograms. And when the dust settles, when we calculate this, we get acceleration equals 3.9 meters per second for every second. This means every second the box, that is the 70 kilogram box, the box's velocity should change by about 4 meters per second. Cool. And that's kind of nice. So now, at that point, you might want to look at everything we've learned concerning constant acceleration real quick. Okay? So you'll recall that we could do a stack of graphs representing the object's motion. Okay? So we could draw a position versus time graph. We could draw a velocity versus time graph. And we could draw an acceleration time graph. That's actually a really nice place to start, because we know that the acceleration in meters per second squared, we know that every second this object is speeding up by about 4 meters per second. So in other words, the acceleration of our object is 4 meters per second squared to the right. And you'll recall that this area under our acceleration graph was our change in velocity. And that should be equal to 4 times t. Right? And the equation of this line here will be a equals 4 meters per second squared, because we have constant acceleration. Every second, whoops, every second, objects, this is a box still, velocity changes by 4 meters per second, right? And then our velocity is measured in meters per second in this case, times in seconds, and position in meters. So the slope of our velocity graph should be 4 meters per second squared. So velocity graph will go up like this, right? And our initial velocity, if we assume our initial velocity is 0, let's say, and then this will be our final velocity. And the difference between our initial and final velocity should be 4t, And this area here would be our displacement, which is the area of that triangle, 1/2 delta V times T, which simplifies to 1/2 times 4T times T. And this is assuming our initial velocity is 0, which isn't always the case. And we could write an equation of this line. Final velocity equals A times T, right, plus initial velocity. And there's a vector equation right there. And then this graph should be curving upwards because the velocity is increasing. So this graph has to increase steepness. So we could write our equation of this, which is going to be position equals initial velocity times time plus 1/2 AT squared. This comes from this area here. In general, delta x is going to be this triangle plus the rectangle. The rectangle is here only if we have an initial velocity, plus the triangle is 1/2. The change in v here is simply AT times t. So in other words, displacement is initial velocity times time plus 1/2 AT squared. And if you solve that for position, final position, you'll have to add x naught plus v naught t plus 1/2 AT squared. Now you have the full expanded version. So this is delta x. That's not really x final, that's delta x. So you have this version of the equation, which is quite common, and you have this version of the equation, and fundamentally they are the same thing. Okay? So this is everything we know about constant acceleration motion. Anyway, hope that was fun, and I hope you have a good night, okay?